Okay, good morning, everybody.
Good morning.
Morning.
I hope you're all doing well. I'm going to start it off by asking, are there any questions? Does anybody have any questions?
Professor, may I ask you about laboratory job? So we have to do this experiment at home, or we just have to, I don't know. Honestly, I don't know how to do that.
So there's three things you do. So for the lab, what you do, and there's going to be 7 of these throughout the semester. So the first one is calibration of volumetric glassware. So you're going to find the information you need for that. It's actually in 2 places. One, the syllabus, which is in Blackboard, has a link to videos, which are on YouTube. Okay. So what you want to do is you want to go to the syllabus and look for the section on the laboratories, and you'll see, oh, there's a link for YouTube. And so that link will be a folder of different videos for all the experiment. It's more than we're going to do. There's other videos in there too, but it's got all the videos of the reports we're going to do. So calibration of volumetric glassware, that's the one you're doing. So the second place you want to look is in Blackboard under course content. Okay, and you're going to see 2 things. You're going to see what's called a procedure, and then you're going to see what's called a report sheet. Okay, there'll be 2 documents there for this experiment. So the first thing to do is just download both of them. And the procedure, you just read it over. Okay. So you read it. So step 1, read the procedure. Okay, that's in the course content. Step 2, watch the video. Okay. So again, that's the video that you see there on YouTube. And the videos are pretty lengthy because essentially the instructor goes through the entire experiment. So it's going to be like an hour, hour and a half, something like that. Okay. And they're going to give you a little background lecture too sometimes, and they're not all done by the same instructor. So, you may have one preference over another for how they're describing it, but you're going to watch them do it. And then here's what you do. The report sheet, that one right there, that's essentially a Word document. The third step is you're going to fill out the report sheet. Okay, so you've already downloaded it. So that's that second form that's there. So the first one's the procedure. You're not going to turn in the procedure. That's there for you to read it over and see how they're doing it. It has a little bit of theory in it and stuff like that. But when you do the report sheet and you fill that out, you may want to refer back to the procedure because it has information in there. It's almost like a little textbook, right? So you can use that to get information to do the report sheet. And then the report sheet, it's typically 2 pages long, you're going to turn this in. You're going to email it. And all the directions of how you submit it are given on the sheet itself. It tells you what email address to send it to. It tells you what you need to put in the subject line of the email. And you're going to attach it. It'll be an attachment like a Word document. And then you turn that in. So this is what you're going to turn in. So you'll watch the video, you'll read the procedure, and then you'll turn in the report sheet. Okay. The deadlines for all the reports, and like I said, there's 7 of them throughout the semester. The first one is this calibration of volumetric glassware. The deadlines are in the syllabus when you need to have those emailed by. And they're also on the actual report sheet. The deadline is actually on the report sheet when it needs to be turned in by. So far, I've put the documents up for the first 2 experiments. So I put these into Blackboard, and then the second one is empirical formula of copper oxide. So I put those documents up as well, but I haven't done the other 5. I saw no need to put the other 5 up yet because it's unlikely someone wants to turn in all the lab reports in 1 week. So those will pop up over time, okay? Roughly every 2 weeks, one of them is due. There's a little bit of variation in there because we have this spring break coming up in a couple of weeks, about a week and a half, actually. So there's a little bit of variation, okay? Does that answer your question?
Yes, thank you.
Great, awesome. I'm glad you asked it because that's actually a little area of confusion for people often. So that's good that you asked that. Okay. Any other questions, anybody?
I'm sorry, can I ask you one more question about our chapters? Let's say we're doing chapter 3 for now, right? And it's gonna be just like a practice, or we're gonna get some points while we're doing this. Let's say if I don't answer right, like don't answer correct, I'm gonna lose some points, or it's just practice before the exam.
So actually, so let me just take a moment to go over the grading in this course. 65% of your grade is the Alex homework. And then 30% are the 6 exams. So that's 5% each. Okay, and then 5% are the lab reports. Okay, so the primary grade you're going to get is based, it's primarily on the homework, to some extent the exams, and then to a little bit the lab reports. So, this will be your primary focus, right? This is what you work on the most. So the way the Alex works is kind of cool. What they do, so what I did was I selected for each chapter, I selected a certain number of types of problems, and they call them topics. Now, chapter 3's got a lot. There's like 28 topics or something like that. There's a lot. The other chapters are a little smaller. Some of them are only 20, some of them are only 15, but the problems get a little harder, so there's fewer of them. Okay, but chapter 3 has a lot of topics. And I think it's 24 or 28, something like that. So what happens is each one of these topics, so let's say you're doing topic 1, you got to get it correct 3 times. And if you get it correct 3 times, you get credit for that problem and you're done with that problem. Okay. And then, so you'll just go through topic 2, topic 3, all the way to topic 28. And then once you've done all of them 3 times correctly, you get 100% on that chapter. And that's going to go into this percentage right there. Okay. So in theory, you could get it wrong. Try it again, get it wrong. Try it again, get it right. Try it again, get it right. Try it again, get it right. And once you get it right 3 times, you're done with that topic. Okay. So you don't really get penalized for getting it wrong. It's not a test. It's a homework assignment. So you can get it wrong. Now, it does have built into the software that if you get it wrong a lot of times and you're just not getting it right, it's gonna warn you and say, look, we want you to go back and read your textbook or something like that and try to get some clarification on this before you try again. So they're going to make you take a break, but you don't get penalized for getting them wrong. The test is a test, right? So once you take the test, here's what I did for the test. I took 10 of these 28 problems and I put them on the test. That's what I did. Okay, someone's like, okay. So I just took 10 of these problems from the chapter. I'm gonna have to mute everybody. If you want to talk, go ahead and mute yourself. There you go. So I took 10 of the problems from each chapter and then turned them into exams. So you're going to just kind of redo 10 of the problems that you did on the homework for the exam. Okay. How about that? Is that an answer for you?
Yes, thank you.
Excellent. All right. So again, I do recommend that when you do the homework, try to make it kind of like they recommend you do exercise. It's better to exercise 20 to 30 minutes a day than for 2 hours once a week. And the same would be true with the homework. So I would try to do 2 to 3 topics every day. And if you can do 2 to 3 topics every day, you're gonna, you'll just get it done, you know. And the exams are based on the homework, but sometimes it's a good idea to do a little review before you do the exam, right? Because the exam is like you only have like an hour to do it. You got to get 10 problems and all that. And so what I would recommend for the way you schedule your days is try to finish the homework like 2 or 3 days before the exam is opened up. And that way you can take those 2 or 3 days, and there are practice exams on ALEX. So you've got exams, but you also have practice exams. So the practice exams, I don't grade them. They're not part of your grade. They're just there for you to practice to kind of get ready for the exam. So do the homework, give yourself a couple days, do the practice exam. Each exam has a practice exam. And the practice exams are longer than the actual exam. So there might be 20 problems in there instead of just 10, but they're in there just to give you more practice. And so you can do the practice exams as many times as you want, get clarification on things, and get feedback from me, and then you can take the exam. And, I'll say one thing about the exams is that ALEX does the grading on the exams, and it's not very forgiving. If you get one little thing wrong, you get the whole thing wrong. But what I do after everybody's taken the exam is I go back and I kind of grade it by hand. So I look at what people got wrong and then give partial credit for certain types of problems. So you might have a question where there's like 3 or 4 parts. If you get one part wrong, it gives you a 0. But if there were 3 parts and you got 2 of the parts right and 1 wrong, I go back and I can enter in that you got 2/3. So you get 6.7 points instead of 0 points. But do the homework, do 2 to 3 topics a day. Based on your schedule, you may not be able to do that, but at least try to spend 4 days a week doing it, so that you can do maybe 5 topics today and 4 topics Friday and 2 topics on Sunday, whatever your schedule works out. You have to work that out for yourself, but that's what I would recommend. Try not to put it all off, because if you put it all off, you'll just get overwhelmed. Okay. Speaking of the ALEX homework problem, let's talk about section 3.6. And if we have time, we'll get into 3.7. We might have time for that. I'm going to open up the ALEX problems, and I'm going to take a look at section 3.6, which is called calculations with balanced equations. So it's calculations and the particular problem I'm going to look at here is called using a chemical equation to find the moles of a product from moles of a reactant. Okay, so that's the title of the type of problem. Now, this one's a pretty involved problem. Let me minimize this a little bit. Okay. Slide this over here. And there we go. I just want to be able to see if anybody comes in. Okay, so for this problem, what they're going to do is they're going to give you the name of the compound, and then they also give you the formula at least. So for this one, they tell you that ammonium perchlorate, and then they give you the formula. So NH4ClO4 is a powerful rocket fuel. So it's a rocket fuel. Okay. And it decomposes into nitrogen. Now they're nice enough in this problem to give you the formula for nitrogen, N2, gas, chlorine gas, and oxygen gas. And there's a lot of ands here, and water vapor. Okay, so I'll put that in there, water vapor. Okay, so here's what they're saying to do. Calculate the moles of chlorine produced if 0.800 moles of ammonium perchlorate decompose. Okay, so this is an issue of a balanced chemical equation. And then we're going to have this idea of how we do calculations with balanced chemical equations. So we talked about how we balance back in section 3.3. Now we're going to use a balanced equation to do some calculations. So let's start off by writing the reaction. So ammonium perchlorate decomposes. That means it breaks up into something. It breaks up into usually lots of little things. So that means it's the reactant. If something decomposes, that means it's the reactant. Now, I forgot to put it, but it actually says in the question that it's solid ammonium perchlorate, so solid. Decomposes into, so now you write your arrow to say that it's getting converted into. The arrow says you're producing products, you're making products, okay? So it's going to decompose into 4 different things. N2, gas, right? So G for gas. Chlorine gas, Cl2. Oxygen gas. And then water vapor. So vapor is just another word for gas. Okay, typically we don't call it gaseous water or water gas. We typically call it water vapor, okay? So let's start by balancing the equation. Now that looks like a pretty complicated equation, so let's see what happens. I'm gonna start on the nitrogen. There's 1 nitrogen on the left and there's 2 on the right. So I'm gonna put a 2 here so that we have 2 nitrogens. Now I'm gonna go to the next element. The next element is hydrogen. So nitrogen, now there's 8 hydrogens on the left, right? Because you have 2 and a 4, right? 2 times 4 is 8. Over here, there's only 2, so I'm going to put a 4 over here. So now we have 8 hydrogens on both sides, right? 4 times 2 is 8. So the third element is chlorine. There's 2 chlorines on the left, right? Because you've got the 2 here. The 2 refers to everything in there. You've already got 2 over there, so you're done. And then the oxygen, there's 8. And then over here, we've got 2 and another 4, so that's 6. But we don't want to change this number because that would change hydrogen, so I'll just put a 2 here. 2 times 2 is 4, plus another 4 is 8. And even though it's a pretty complicated looking equation. The balancing is actually pretty straightforward, right? There's no what we call interfering coefficients. There's no fractions that we need to put in there. I just started with nitrogen, then hydrogen, then chlorine, then oxygen, and it worked out well. But we only need to know two of these coefficients. We only are concerned with this problem with this one and this one. And here's why. Calculate the moles of chlorine. So how many moles of chlorine are produced if 0.800 moles of ammonium perchlorate reacts? So I'm going to write 0.800 moles here. Okay, so they're asking us to find the number of moles of chlorine that are produced from the decomposition of 0.800 moles of ammonium perchlorate. So what I'm going to do, I'm going to save this here and then bring up another slide, and I'll come back to this calculation in just a moment. What I'm going to do is I'm going to say the following. I'm going to take this one, and just to make things simple, I'm going to ignore all the other products because they're not asking us about the other products. They're only asking us about these two substances. Okay. Here's essentially what happens. If you have one of these ammonium perchlorate, so I'll put parentheses around it just to say, hey, look, suppose I look at this unit here. There's one chlorine in there, right? But we needed two chlorines over here. So what happens is two of the ammonium perchlorates react. Two of them will give us two chlorines, which now gives us a chlorine molecule, which has two chlorine atoms in it, right? Two atoms of chlorine make one chlorine molecule. So that's why the two is, that's one reason why the two is there. The two is there to say, look, if we're going to have two chlorine atoms here, we got to have two chlorine atoms here. And the only way to get that is to have two of the ammonium perchlorates. So let me show you a little picture just to kind of give you an idea what I mean by that. So I'm going to show you the structure of ammonium perchlorate. So that's the NH4. This is called ammonium. And the whole thing is positively charged. It has an electrical charge. It's called a cation. C-A-T-I-O-N, like cat ion, right? Charged particles are called ions. And if the charged particle is positively charged, it's called a cation, cat for positive. The ammonium is attached to a perchlorate ion, which is a different ion. It's kind of a funky ion here. Looks something like this. Don't worry about the double bonds that I put in there. We'll talk about that later in the course. And that one is called the perchlorate anion. An anion is a negatively charged ion. So this is an example of an ionic compound because it has a positively charged ion, a cation, attached to a negatively charged ion, an anion. Now, the thing about rocket fuel is that what happens when rocket fuel burns is just all the atoms get ripped apart in highly energetic processes. That's why rockets are so good or that's why rocket fuel is so good for producing rockets. A lot of energy involved. So essentially these molecules get ripped apart, these ions get ripped apart, and this chlorine atom is ripped out of the molecule, out of the compound, as a separate atom. And so what happens is if you have two of them, right, the coefficient refers to how many of these ions you have. So I'm going to draw a second one, right? Because we have this two here. So here's the first one, and then here's the second one. And it's fascinating stuff to talk about how these things get ripped apart. But that's essentially what happens. This atom gets ripped apart as well. It's pulled out of the whole thing. The oxygens combine with the hydrogens to make water. The oxygens combine with each other to make O2. The nitrogens combine with each other, right? Here's a nitrogen, here's another nitrogen. They combine with each other to make molecular nitrogen. And what happens is these two eventually collide with each other. and you get 2 chlorine atoms bonded together, which is Cl2, right? When you have 2 atoms bonded together, we just write it as the symbol with a 2. So there's your product, right? And so the reason that we have that 2 in front of there is because if we're going to get this, we need to have 2 chlorine atoms to pull off together, to combine together to form that chlorine molecule. So now here's what happens. We're just going to do really what's called a proportionality. And that is the following. Every time 2 of these reactants react, get used up, are utilized in the reaction, every time 2 of the ammonium perchlorates react, okay, you get 1 chlorine molecule, right? I'm actually going to explicitly put 1 there. Another way of thinking about this is, suppose I don't have 2 molecules of ammonium perchlorate. Suppose I have 2 moles. Remember, mole is just a large number, 6 times 10 to the 23rd, like a dozen. If I said I have 2 dozen donuts, that means 24 donuts, right? So I could say that, you know, I'm going to combine 2 donuts with a piece of ham and make a sandwich out of it, right? So same idea here. 2 moles of ammonium perchlorate is going to give us 2 moles of chlorine. That's essentially the logic of these particular problems. I'm sorry, 1 mole of chloride, right? 1. Okay, right? If you have 2 of these, that means you have 2 chlorine atoms. That's going to give you 1 molecule here. So what I'm doing is I'm connecting it as moles now, just like I would do dozen. If I said, look, 2 of these give you 1 of those, I could also say 2 dozen of these will give you 1 dozen of those. Or I could say 20 of these will give you 10 of those. Or I could say 200 of these will give you 100, right? It's a proportion. The proportion is 2 to 1 or 2 moles to 1 mole. So that's the logic you're going to use in these problems. Is you look at the balanced equation and you relate the substances that they're asking you about to moles, okay? So let me save this. I'm going to come back to our problem in just another minute, but let me show you another example. I'm going to really drive this point home about what this means, the interpretation of the balanced equation. We could interpret this as meaning 1 molecule of N2. Why 1? Because there's no number written there, so it's implicit that that's a 1. That reacts with 3 molecules of H2. So now notice I put an equal sign there. So the reason I put an equal sign there is because an arrow is sort of like an equal sign, and it allows us to do calculations. So the interpretation of this would be that when 1 molecule of N2 reacts, the equivalent amount of hydrogen would be 3 molecules. It'll react in a 1 to 3 ratio. So I'll use an equal sign to make it calculatable. Likewise, we'll produce 2 molecules of NH3. Okay, so again, I'm going to use an equal sign there because we want to talk about equivalencies. In this reaction, if 1 molecule of N2 reacts, 2 molecules of NH3 will be produced. Now, I could also say 1 dozen molecules of N2 react. Right? A dozen is a unit. And I could say 3 dozen molecules of H2 react. And I could say 2 dozen molecules of NH3 are formed. But dozen is not helpful in chemistry because the dozen is such a small number. 12 is such a small number, it doesn't help us. What really helps us for measuring amounts of materials that we really deal with is the mole, because the mole, you know, a dozen is 12. A pair is 2. But a mole, that's a helpful number because it's such a large number. So it's more useful to interpret the balanced equation in terms of moles. So I'm going to write it this way. 1 mole of N2 reacts with 3 moles of H2, and that produces 2 moles of NH3. Okay, that's the logic that we're going to use here. And this is more useful than the other interpretations, meaning the ones up here, because remember we have this relationship between mass and moles. If we know the number of moles of something, we can figure out the mass. Or if we know the mass, we can find the moles. We can do either way. So the mole is more useful. So that's why these problems all involve moles. Okay. So now I'm going to save this one. I'm going to come back to our little problem and show you how to do the proportionality. This one right here. Okay. Okay. So I'm going to erase this here. Actually, you know what? Let me save that. Let me go back to the first one. Here we go. That's the one I wanted to look at. Let's come back. What we're given is 0.800. I'm sorry. I'm having a little technical challenge here. Just give me a minute here. Every once in a while, the pencil I'm using dies. So let me just give it 30 seconds of charging. Let's see if that works. Okay. So we're going to take this number. Oops. There we go. So we're going to take this number here. This is what's given. And I'm going to write it out as NH4ClO4. There we go. Okay. The question is, how many moles of this are going to get formed? So here's how I'm going to do it. Think of, you know, just to give you a sort of a practical analogy, think of this like, hey, it takes 2 wheels to make 1 bicycle. Okay. So if I had 800 wheels, I could make 400 bicycles, right? Half of 800. So here's how I'm going to do this. I'm going to take my 0.800 moles of the material they gave me, and I'm going to multiply that by what I want. So that's this one here. I'm going to use the coefficient, and then I'm going to divide it by this coefficient. Okay, now take a look. I'm using dimensional analysis, the units and all of that, but the logic is essentially bicycles, right? If I had, I know this is 0.800, but imagine bicycles, it could be 800. 800 wheels or 800 tires, how many bicycles? You would multiply it by 1/2, right? Because you get half as many bicycles as you have wheels. So that's the logic here. Every time 2 of these react, you only get half as much, 1 of those. So I'm putting this coefficient here, and I'm putting this coefficient down there. What I want divided by what I have. So 0.800 moles divided by that number. So 0.800 times 1/2 would be 0.400. And then the units would be up here, mole CO2. And so it's very simple, right? The actual calculation was ridiculously simple. My explanation for it took almost a half hour, but I really wanted to go over kind of the logic of how we're doing these calculations. You're essentially taking the balanced equation, and then you're saying, how many moles of this do we get out of how many moles of this we have? You got to use really 3 pieces of information. You need the given data. That's the data they gave you. Then you need the coefficients, and you're going to multiply it by the coefficient you want divided by the one you have. Okay, let me show you another example. Okay, here's a combustion problem. So again, same type of problem. So in this one, they tell you, they're talking about gasoline. A major component of gasoline is octane. So actually, let me come over here. Let's try this, just so that you can see it a little bit better. And I'm going to there we go. Move this over here. There we go. So hopefully you can see this a little bit better now. Using a chemical equation to find the moles of product, okay? So a major component of gasoline is octane, C8H18. So they give you the formula. When liquid octane is burned in air, it reacts with oxygen gas, O2. That's what's one of, that's the reactant in air essentially, to produce carbon dioxide gas and water vapor, right? So they're giving us all the substances. They don't give us the formula for carbon dioxide, but that's CO2. Calculate the moles of oxygen needed to produce 2.4 moles of water, and be sure your answer has a unit symbol, just meaning you put units in it. And if necessary, rounded to 2 sig figs, okay? So let's screen portion. Oops. Okay, I'm sorry here. Ooh. Oh, here we go. Sorry. There we go. Excellent. Okay, sorry. All right, so let's try this again. So we have octane, and they give us the formula C8H18. And they tell us that it's liquid. That's given. And it combines with oxygen gas to form carbon dioxide. Now, carbon dioxide is CO2, and they tell us it's a gas. And then they give us that it's liquid water. Actually, it just says water vapor. I'm sorry, it says water vapor. So again, gaseous water. Okay, so they gave us that information, and then they ask us to calculate the moles of oxygen needed to produce 2.4 moles of water. Okay, so water is of interest and oxygen is of interest. And in fact, they tell us that 2.4 moles of water is what's going to be produced, okay? Let me come back over here. There we go. Okay, so here's how we're going to go about it. First, we have to balance the equation. Okay, so let's start. I'm going to start by noticing, I'll just start from the left and move to the right. Oxygen's all by itself, so do that one last. Okay, so we have 8 carbons here. We only have 1 here, so I'm going to put an 8 in front of the carbon, right? That'll give us 8 carbon dioxide, so now we have 8 carbons. We have 18 hydrogens. We have 2 here, so we just figure out what times 2 equals 18. 9 times 2 equals 18, so I'm going to put a 9 here. Okay, so the hydrogen is done. The only thing that's not done is the oxygen. So now let's be careful. This is one of those problems where you have interfering coefficients. We talked about that last week. So the way to deal with this, the way I deal with it is I say, okay, on the left side, we've got 2 oxygens. So this is dealing with oxygen. We can put a coefficient here. We haven't put a coefficient here, right? So we can put something there. I'll call it n for the coefficient. So 2 times n, right? 2 times n. Right now, n is a 1, so we have 2 atoms. But if it was a 2, we would have 4 atoms. If it were a 3, we would have 6. On the right side, we've got 16 here, right? 8 times 2. So 16. Actually, let me be a little bit more. 8 times 2, right? 16. And then 9 times 1 here. Right? Why is it a 1? There's nothing written there, but it's implicit that that's a 1. So on the right side, we've got 16 plus 9 is 25. So that means what we have on the left side has to be equal to 25. Or at least it would be balanced if it were 25, right? So how do we deal with this? Well, we just need to find out what that coefficient is. So we say, let's divide both sides by 2. Because if you divide the left side by 2, you get n. So n is equal to 25 halves. So that means if we really want this to be balanced, we could simply put 25 halves there, and that would be balanced. And by the way, if you did it right there and you use the 25 halves in your calculation, you'll get the right answer. It will perfectly work. If you feel uncomfortable with fractions, you can then do the final step, which is to multiply everything by 2, right? If you multiply all the formulas by 2, you'll also still have a balanced equation, but it will get rid of that fraction. And so as far as I'm concerned, it doesn't matter which one you use. You're going to get the same answer no matter what. Okay, so this balanced equation will work for the calculation. This balanced equation will work for the calculation, doesn't matter. Now we use the logic of what we talked about. This is the substance that we know about. This is our given information. So I'm going to write it this way. 2.4 moles of O2. So you take that given information, and then you say, which one do we want? We want to know the oxygen. So I'll use the balanced equation just to. So it's 25 of those for every 18 of those. Okay. I'm wrong. It's not 2.4 moles of oxygen. It's 2.4 moles of water. I don't know why I did that. It's water, right? That's what they told us. Okay. So I'm going to multiply that by the one that we want. They asked us for oxygen. So I'm going to take 25 moles of O2. And then I'm going to divide that by the one that we were given, which is 18. Again, you'll get the same answer if you use the 9 for water and 25 halves for oxygen. Just mathematically, it'll give you the same answer. Okay. So now the moles of water are gone, and that's going to give us moles of oxygen. Okay. So let me run that through a calculation. So we have 2.4 times 25 over 18. And well, yeah, it's about 3.3. It says to round it to 2 sig figs, so 3.3 moles of O2. Okay. And there you go. So again, you got to balance the equation. That's going to be some effort perhaps to balance the equation. But once you got the equation balanced, the actual calculation is pretty simple. You take the number of moles of the substance they give you, and then you multiply that by the coefficient of the one you want divided by the one you have. and then that'll give you the moles of the one you want. Okay. And you could do any relationship in that equation that you want. You could do carbon dioxide and octane. You could do oxygen and octane. You could do water and carbon dioxide. Any relationship will work. Okay. So let me show you one more of this type. And that is, I'm gonna write the equation here. And I'm not going to worry about the states of matter here. I'm just going to put the equation, and I'm going to say, suppose 3.2 moles of CO2 are produced. How many moles of water are produced? How many moles of C6H12O6 react? Okay, so there's really two questions in there, right? It's really two questions. So let's begin. Like I said before, we're going to balance the equation first. So I'm going to start with carbon. There's 6 carbons over here. There's only 1 over there, so I'm going to put a 6 in front of it. So now we have 6 carbons. There's 12 hydrogens here. And again, I'm putting oxygen off for last because oxygen is non-interfering here. There's no interference with other elements right there. So we'll do that last. So you have 12 hydrogens on the left. So put a 6. 6 times 2 is 12, right? So you have 6 waters. And then we're almost done. We just got to do the oxygen. There's 6 over here. So let's do this. We're going to put a coefficient here. I'm leaving that oxygen for last. So you got 6 oxygens. So this is oxygen. And then you have oxygen here. So plus 2n, right? 2 times whatever that coefficient is going to be. Now, why do I know that we're going to have to change that number? Because we have so many over here. There's a lot of oxygen over there. 6 times 2 plus 6 times 1. Now, if you're tricky, if you're careful about this, think mathematically, you have 6 on both sides. 6 times 1 is 6, and 6, that you could cancel those and make it a little simpler. So you got 2n equals 12. And then n would be 12 over 2, which would be 6. So that tells you the 6 here. Okay. So now we've got our coefficient. So here's the 2 questions. The first one is you got 3.2 moles of carbon dioxide. How many moles of water are produced? So there's your water. So you take the one that you want, so times 6 moles of water, and you divide that by the one you have, which is this one right here. 6 moles of carbon dioxide. And look what happens. You get the same answer, 3.2, right? But that makes sense because look what happens. You produce the same amount of water as you produce carbon dioxide. So you should get the same answer. If they have the same coefficients, you're going to have the same answer for each of them. Okay. It's only when the coefficients are different that you'll get different numbers. And then the second part was how many moles of, this is glucose, are going to react. So again, you take the one you're given, 3.2 moles of carbon dioxide, and you multiply that by the one you want, 1 mole of glucose, and you divide that by the one that you are given, which is the carbon dioxide. So 6 moles of CO2. Okay, so moles of CO2 cancel, and you got 3.2 times 1 divided by 6, and you get 0.53. And there you go. This is pretty basic, right? The calculation is not that complicated. You're just using those coefficients and the given number of moles of substance to figure them out. Okay. Now, typically, we deal with numbers in chemistry in grams, mass units, not in moles. So other types of problems will involve using grams. Okay. So let me show you the next type. I'm going to come over here. Let me, oops. There we go. Let me come over here and share this screen. There we go. Okay, so that's somewhat visible. So this one is called solving for a reactant using a chemical equation. So in this one, they say that ammonium perchlorate, again, that's the one we just looked at, the first one we looked at, is the solid rocket fuel used by the space shuttle, which is no longer used. It reacts with itself. Isn't that interesting? It reacts with itself to produce nitrogen, chlorine, oxygen, and water, and a great deal of energy. What mass of water is produced by the reaction of 9.7 grams of ammonium perchlorate? Answer to 2 sig figs, okay? So see how this problem is different than the previous one? In this problem, we're given grams, and it asks us for what mass. So now we're doing mass conversions. So it's similar to the one we did, just be careful, it's got mass units. So what I'm going to do is I'm going to write our balanced equation again. You know, luckily this is one we already looked at in terms of the balanced equation. And we had N2 plus Cl2 plus O2 plus H2O. This was a 4, and I guess that was a 2, right? 4 plus 4 is 8. There we go. So there's our balanced equation. So in this particular problem, they said that 9.7 grams react. And what they're asking us is what mass of water produced, what mass of water is produced in this particular reaction, okay? That's the question. And so here's what we're going to have to do. This one's a little bit more involved in terms of the calculation. And here's what we have to do. This is given in grams. So our first step will be to use the molar mass. Remember what we said is that if you're given the mass and you want to find the number of moles, you divide by the molar mass. That's what we talked about earlier this week, right? And this will give us the moles that react. Okay, divide something by its molar mass and that gives you the moles. Then in our second step, what we're going to do is we're going to use the coefficients just like we did before. It's 4 moles of water for every 2 moles of ammonium perchlorate. Okay, that's that ratio that we were just looking at in the previous 3 problems, right? The 2 is the ammonia, so you take the moles of what you're given. So here we're going to have moles of this. That's what we have when we divide by the molar mass. Then we're going to multiply it by that ratio, 4 to 2. And that's going to give us the moles of water produced. Okay, that in a sense, that's the answer. But they ask us for the mass. So we got to do one more step. We multiply by the molar mass of water. And that will give us the mass, grams of water. Okay, so this is 3 steps. The first is to convert grams to moles. Now we can use the balanced equation and the coefficients to find the moles of water. Right? The produced, we're talking about water is what's produced. And then multiply by the molar mass to get the number of grams. So let's go through it. I'm going to take 9.7 grams of ammonium perchlorate. Now, I don't know what the molar mass of ammonium perchlorate is, but I'm going to calculate it. Nitrogen is 14.01. And hydrogen is 1.01, but there's 4 of them. So 4 times 1.01. There's only 1 chlorine. Chlorine weighs 35.45. And then there's 4 oxygens. So 4 times 16.00. And you get 117.50. Okay, so remember, divide by the molar mass. So how do we divide? We say 1 mole of ammonium perchlorate. Divide that by the molar mass. That's going to give us the moles of ammonium perchlorate. That's our first step there. So 9.7 divided by 117.50, and you get, it's a small number, 0.08255. Okay, so all we're doing differently from the previous problem is we're just adding in divide by the molar mass so that you have the moles to use that ratio. So now, second step, we're right here. So in fact, I could probably put right here, we have 0.08255 moles, right? That's what we have right here, okay? Now we're gonna multiply by that ratio, just like we did in the previous 3 problems. So 0.08255 times 4 moles of water over 2 moles of ammonium perchlorate. Okay, so for, units cancel, you're essentially multiplying by 4 halves. So times 4 halves is now 0.1651 moles of water. So 0.1651 moles, right? So we've now got the moles of water. And then just like we talked about in section 3.4 about moles and molar mass, if you want to go from moles to grams, you multiply by the molar mass. Now, what's the molar mass of water? You may have done enough problems that you know it's 18.02. Okay, molar mass of water is, there's 2 hydrogens, so 2 times 1.01, and there's 1 oxygen, so 1 times 16. So that's 18.02. So our third step is we multiply, we're converting from moles of water to grams of water. So multiply by the molar mass. So 18.02 grams for every 1 mole. Okay. Remember, the molar mass is how much mass something has if you have 1 mole. It's like, how much does a dozen eggs weigh? You could have like a kind of a molar mass of eggs. You could say 1 dozen eggs weighs, I don't know, 0.95 pounds, right? And extra large eggs, 1 dozen extra large eggs weighs 1.05 pounds or 1.15 pounds. So that's essentially what the molar mass is, how much a unit, how much 1 mole weighs. So multiply that by 18.02, and you get 2.975 grams, sorry. Let's do the dimensional analysis. Moles of water divided by moles of water, and we're left with grams of water. So now we have our answer. It's 2.975, but in the question it said to round it to 2 sig figs. So let's look at this rounding. 2 sig figs means you got 1 here, and there's a second one there. But the number behind the 9 is 5 or greater, so that means we have to round up, right? So that means we're going to round the 9 up into a 10, which means we have to carry a 1 over to the 2. So you get 3.0 grams of water. Okay, so now we can put over here, our answer is 3.0 grams of water. So now here's how many grams of water were produced. If they asked us for oxygen instead of water, what we would do is we would find the moles of ammonium perchlorate, just like we did. Then we would use the ratio 2 moles of oxygen for every 2 moles of ammonium perchlorate. So this ratio would be 2 to 2 here. And that would give us the moles of oxygen. Then we would use the molar mass of oxygen, 32 grams per mole, right? 2 times 16. 32, that would give us the grams of oxygen. So we could do this one too. We could do the chlorine. Again, the ratio here is 1 to 2. And then the molar mass of chlorine is different. It's 70.90 grams per mole. And you could do each of these if you wanted to. Okay. So that's the two types of problems that are in section 3.6. And we have one more section in this chapter, which is 3.7. So tomorrow, I'll go over any questions that people have. And then I will look at 3.7, which is called limiting reactants, which is kind of related to this type of problem. It's pretty similar. There's just one extra level of complexity to it that we have to consider, but it's a similar type of problem. So I would recommend, I don't know, if you haven't done a lot of these and you're uncomfortable or unconfident in doing these, maybe just kind of have this little flow chart for yourself. I find it helps me anyways for kind of thinking about it. Typically, you're given the grams of one of the materials. In this case, it's a reactant. Divide by molar mass to get moles. Use the balanced equation and the coefficients of the two materials you're interested in to find the moles of the substance you're interested in. And then use its molar mass, you multiply by its molar mass to convert it to grams. Because typically these problems are set up. They give you the grams of some substance, A, B, C, or D, and they ask you for the number of grams of another substance. I'll call it B, right? So you're given the grams of one and asked for the grams of another. And so this little flow chart can be helpful for that. Okay. Thank you, everybody, for being here. I'm going to post this to YouTube over the next hour or two. Sometimes it takes a little while for YouTube to post it, but it should be done within an hour or two. And reach out to me, send me a text or something if you have any questions. And we'll be here tomorrow. Tomorrow's Thursday, so we'll be here to talk about limiting reactants. And maybe if we have time, we'll get into chapter 4 a little bit. So have a great day, everybody.
Thank you. Have a great day.
Thank you.
Thank you.